This video is going to explore the work-energy theorem, and it's going to explore the connection between work and energy. Now, what is work? Work is the transfer of energy by mechanical means. So that's what work is. If you do work on an object, you are transferring energy to it. And if we look down at our equations, our work equation is work equals force times distance. It also equals our change in energy, our change in total energy. The symbol for work is capital W, and the units is joules. So joules, same units as energy. So if you see any number with the units of joules, it's going to be either energy or work. Okay? So you're going to have to look between them and compare and say, okay, which one are you? Now, work equals force times distance. This is important. Let's say I ask you to move a heavy box, a very, very, very heavy box, and you push on it, and you push, and you push, and you push, and it doesn't move. If it doesn't move, it doesn't matter how much force you put into it, you have done absolutely no work. So if you have a little brother or sister and you tell them, I'll tell you what, I'll pay you for your time. Work at moving this immovable object. I will pay you $1 for every, 10 minutes of work that you do. Well, they can sit there and push on it all day, and you can point and laugh all day. If they don't move it, they've done no work. Okay, so force times distance is your work. Now let's look at an example. You are driving along in your brand new, totally awesome car. You are on a flat stretch of highway, with no cops, of course. You put the gas down, and the car's engine applies a force of 55 newtons for 100 meters. How much work was done on your car? So how much work did that engine do? Well, work equals force times distance. So it equals a force of 55 newtons times a distance of 1,000 meters. So that's 55,000 joules of work. Let's look at another example. Now this example is in the vertical. Vertical is a little bit different in that you have to recognize a certain fact. That if you're lifting something, your force applied has to be at least equal to force of gravity. Okay, your average force applied has to cancel out force of gravity. So if you have a 5 kilogram block, then you have to apply a force equal to that of gravity. So your force applied has to be equal to mass times gravity. So 5 times 9.81. So 49.05 newtons has to be your force. Now sometimes they're nice and they tell you the weight of the box. They say it's 5 newtons. If they give you the newtons, woot woot, you don't even have to solve for it. They give it to you. But if they give you the mass, then you have to solve for the force. Now work equals force times distance. So you had to apply a force of 49.05 newtons to lift it in the vertical. Remember, this is vertical. And you lifted it for a distance of 2 meters. So you lifted it 98.1 joules of work to lift that block. Okay, so that's work. Now the work-energy theorem states that work and energy are two sides of the same coin, which means doing work results in a change in energy, and energy is the ability to do work. So let's think about this logically. You have a block here. It's sitting on the ground. It's just sitting there, so it has no kinetic energy, no potential energy, because it's at 0. You lift it, and it sits up there. It now has potential energy. Kinetic energy can still be 0. It can still not be moving. But it has a change in total energy. It went from 0 total energy to an energy total equal to its final potential energy, because it's still just sitting up there. So it gained energy. How did it gain energy? I told you energy is conserved. It's neither created or destroyed. What happened is work was done. You did work to lift that block. It gained energy. The energy didn't go poof. It gained it because work was done, and that's the work energy theorem. If I do work, energy is changed. The total energy is changed. So energy conservation still works, because if you include me in the system, then my energy becomes part of that. Okay? And that's why you have that whole work equals change in E total in your reference table. The work equals the total change in energy. So you gained energy by lifting the block up. Okay? The block gained energy. Energy wasn't conserved, but it was, because that extra energy came from the work. Okay? Now if you simplify it down, we know that E total equals kinetic plus potential. So your work done equals the change in kinetic plus the change in potential. So you can solve for it that way. We both started at 0, and we ended with the kinetic energy still being 0. So we had no change in kinetic, but we can find our change in potential if you know how much work you did. If you know you did 10 joules of work, well, that's going to equal mg change in h. Your initial was 0, so it's going to equal mgh final. And you can use that to solve for how high it went. Alright, here's another example down here. Let's look at this real quick. You're throwing a ball. The ball starts at 0. It has 0 kinetic energy. We're saying it stays at the same height, so we're not even considering potential energy. It stays the same. Okay, it starts with 0 kinetic energy, and then you throw it. You do work on it, and it gains kinetic energy. So before it has 0 kinetic energy, you do work, and it ends up with kinetic energy after. And it flies through the air with lots of kinetic energy. But then when it's done, after you've caught it, after you've caught the ball, it has 0 kinetic energy. Well, how does that happen? Well, you did negative work on it. You took energy out of it and absorbed it into yourself. Okay, so work is your change in energy. Let's look at an example in the vertical. A 1.5 kilogram book, so mass equals 1.5, is sitting on a shelf. I apply a force of 15 newtons to lift the book over a distance of 3 meters. How much potential energy did the book gain? Okay, so it gained the amount of energy equal to the work you put in. So you solve for work. Work equals force times distance. That equals 15 times 3, which equals 45. So it gained 45 joules of potential energy. Now, if the book initially had a potential energy of 5 joules, what's the final height of the book? Okay, well, work equals your change in energy, which equals change in kinetic plus change in potential. Kinetic didn't change, so 45 joules equals your change in potential. Now, change is final minus initial. So if it initially had 5 joules of potential energy, so we know our initial, so we know 45 equals mg HF minus 5. Now if we can take away this m, this g, m is 1.5, g is 9.8, so 9.8 1 times 1.5 gives us 14.7. Add 5 to both sides. 50 equals 14.7 HF. And you get the final height is 3.4 meters. Okay, make sure you don't forget to complete your homework. Write down any extra notes. This is kind of a tricky part, an idea that your work equals your change in energy. Write down any notes you need to help you remember. Good luck on your homework.